Think forward. Think Research Channel.
The opinions expressed in the following program are strictly those of the speaker. They do not necessarily reflect the views of the National Science Foundation.
From the National Science Foundation, where discoveries begin. This is Frontier. Discussions of today's most exciting research subjects by distinguished scientists and engineers working at the frontiers of knowledge.
I want to start off by saying that our center is, as Lynn pointed out, Biomimetic Microelectronic Systems, and it's really a partnership between Caltech, USC, and UC Santa Cruz. I'm the director, and Jerry Loeb is the deputy director. And what we're doing here is taking this concept even beyond vision and saying, can we restore neural function through these implants? And often you're left with, for example, you could see reanimating paralyzed limbs. You often have a spinal cord injury. Can we help patients such as this? Here you can see trying to restore cognitive function. There's an area in the brain that looks like this. It looks like a purple banana. It's a banana-shaped organ called the hippocampus, where short-term memories are converted into long-term memories. And can we actually help this area with these implants? So wherever there's a circuit or a synapse that's broken, can we bridge it with microelectronics? And of course, we'll spend a lot of time about restoring sight. So this area is very exciting because the central nervous system and neurons, once damaged, they're very difficult to heal, if at all. In the emergency room when I was an intern, you would see all sorts of injuries. You'd see people come in bruised, bleeding, broken legs, etc. They would all get better, but they would still be left with either a blind eye or other neurological problem. So the challenge is we've picked these three areas of movement, vision, and cognition in our center and trying to address these through these implantable devices. And our vision is that tomorrow's microelectronic systems will interface directly with the remaining host that is still working and enable the blind to see, reanimate paralyzed limbs, and restore cognitive function. As you can see, for the eye, which I'll focus the remainder of the talk, we were talking to just the recipient of a cochlear implant here, and you can see this device, which is used for the hearing impaired. But clearly, you can't put this sort of a device in the eye. And these devices are very limited in terms of how many channels, or how well it can interact with the neurons. And so, although this is a wonderful continuum where we've gotten to implantable devices, it still leaves a significant gap. And in order to do any of these things, you have to have a real bridge between fundamental sciences and biology and engineering to make this happen. And we call this area neural prostheses. So that's the term we use for these implants. And I just tallied up the last time how many different disciplines are involved, and you can see clearly, and some of this is from my own experience, and one of the reasons why I went back to get an engineering degree after I had finished medical school and was just about to enter internship and residency, because I found that I was sitting here often understanding a fair amount about these principles, but I had no idea about digital electronics or any of the integrated chip circuitry or telemetry or powering. In fact, I remember a lot of early discussions with Professor Wen-Tai Liu at North Carolina State, and one of the early grants from Gil was to Wen-Tai and myself, and we just couldn't even possibly come close to communicating. He wanted to know what the parameters were, and I wanted him to just build a device. So ultimately got me interested in getting a degree in engineering. This is the center, and I just want to show you that there's about 30 faculty members from these different institutes. Again, to point out that this is a very large center involving activities from a lot of different companies and also other universities and national labs as well. So if you feel like talking about any of the details, I can specifically refer you to one of the labs or the investigators that is doing it. But you can see here that if you're building something for the retinal test bed, we have 3 different areas we're testing, and you have to be able to develop systems on a chip. So these are the microelectronics. You have to understand how to get power and data in. You have to, for example, if you're taking data from an eyeglass, from a camera and eyeglass, there can't be significant amount of delay, even though there are megabits of information and 256 grayscales. Everything has to be real time, or else the patient or the subject's going to get hit by a bus, for example. So there is no such thing as not real time. And also how to survive these devices in the body. In terms of electronics, this is a real challenge. We're talking about NASA and the constraints they have about taking electronics to space and having those types of hostile environments. But the body is very hostile to microelectronics. 37 degrees, nice warm, saline, water. You know, it's going to corrode just about everything we have. And you can see that in order to develop something for the retina, you really have to piece these 3 areas of technology together. And I'll briefly touch on some of the fundamental research that goes in to develop each one of these technology thrusts. So our vision is to develop these new genre of microelectronics to first restore a mobility type vision. And why? Because that requires lower resolution devices, but then there's a larger population, maybe 10 times as great population, who are legally blind. So they can see large objects, but they cannot read, they can't recognize faces or watch television. And so for those, we would need to develop something that's higher resolution. So a little tutorial on the visual system, and I won't get into too much of the biology, but the front of the eye, the cornea, and the lens are the lensing system. So just like in your camera, they allow focusing on to the back of the eye. And in the back, this is a 1-inch diameter organ. In the back of the eye is lined with this delicate tissue called the retina. And it consists of, it's a multi-layered structure, consists of the photodetectors, the rods and cones, and then a couple of layers of circuitry. So there's some processing that occurs in the eye, and then the information is sent via the optic nerve to the brain. From the optic nerve, you can see here, there's one relay station called the lateral geniculate nucleus, and from there on, the information is sent to the visual cortex here. This area is called V1, as V1 through 6, but this is the primary visual cortical area. So there are lots of diseases. 2 that we'll be talking about is retinitis pigmentosa, RP, and AMD. RP is a genetic defect. And you say, well, if it's genetic, why don't we just fix the genetic defect? Well, it's not that easy because there are more than 100 genetic mutations. So this is a complex genetic problem that's difficult to treat with gene therapy. Macular degeneration is a degenerative condition. So as you start to get into your 60s and 70s, the photodetectors start to get damaged and degenerated. So we're trying to develop devices that would replace the photodetectors. And that's what we're doing. But before, and here's the retinitis pigmentosa, the inherited condition. It has an incidence of 1 in 4,000, so it's fairly common. What happens is in your 20s, you start to lose your peripheral vision, even as early as in your 20s. But by 50 or 60, you've lost all your vision. You're completely blind. So any device that can help with mobility would make a big difference. Here's macular degeneration, the leading cause of blindness in Western countries. You can see it destroys your central vision. So yes, you may be able to read the big E and some large objects, but you're not going to be able to read anything much beyond that. So electrical stimulation is interesting, and it started way back in 1755. I just couldn't help but show you this Leroy's electrical experimentation where he applied a primitive capacitor, sort of like the Leyden jar, and discharged it through his head. I'm surprised he survived this experiment, but It's kind of like Volta did similar things, and there's some very intriguing history to electrical stimulation of human body parts. But he saw a flame rapidly descending. I'm glad he survived it to write this paper. But so electrical stimulation was experimented very early on, but this was the work of Brindley which really brought it to some level of seriousness and implant. And what did Brindley do? Giles Brindley, here in '68, this is a phenomenal achievement. He went for the brain. The eye, we didn't know how to operate into such a small organ. He implanted these. These are not actually the electrodes. These are the coupling, these are the coils that couple to the external stimulator. So these are receiver coils, and there's a transmitter coil that's outside the head, worn as a cap. And so inductively, both power and data are coupled in, and then this is the lead that goes and stimulates these electrodes. Here are the tiny electrodes, and this point, the reason why I point this out is that the part of the brain that allows you to see is not on the surface. Actually, it's sunk into the callicrine fissure, which makes the surgery very tricky and very difficult. You have to slide these electrodes in to enable them to see. Also, you've lost all the processing. I talked about how there's processing in the eye and the lateral geniculate. Well, you're not taking advantage of that. You're going all the way back here, so things get more complicated. And one electrode next to the other doesn't map out that way in the world. So two electrodes in the brain could be mapping very different functions. So you have to do some very complicated real-time algorithms up here. So this was a good approach because, of course, it treats, you can have optic nerve damage, you can have lots of damages that this will address, but it's a more complicated device. So the camera is in the glasses, and so the camera in the glasses then communicates, and this work is still ongoing now. Phil Troik at IIT is working on this, as well as Dick Norman at Utah, and they continue to work at this approach, and it needs to be continued because if you have optic nerve damage, the retinal implant won't work. So you need to continue this work, but it's a much more complicated device. Verart, after he heard about our work in the eye, said, well, why can't we put a cuff electrode around the optic nerve? Why do we have to go into the eye? And there was some very good work by Mortimer at Case Western and others that had built cuff electrodes. And in fact, he put these 4 contact electrodes. The problem with these is that the optic nerve is a bundle. So you stimulate the whole bundle and you can't get the retinotopic layout. I akin the retina to a keyboard. You know exactly where things are. Once you're stimulating the cable, things get much more difficult. And in fact, the second subject didn't generate any useful perceptions, and Verart has, as far as I know, not continued this work. Lateral geniculate. Recall I showed you this is the next relay station. This area is retinotopic. In other words, it is layered, and so there are folks here, Claire Reed is working to put devices and electrodes in there. But again, this is more at the preclinical level, macaque level, to show whether this could work or not. Okay, so that's a quick walkthrough about visual prosthesis. Now, what about retinal prosthesis? Well, I'll talk a lot about our effort, but there's an effort at MIT, Harvard, that has been working on this as well. There's an effort in Stanford, at Wayne State, and then there's some very good international efforts. There are 2 efforts at the University of Tübingen and Fraunhofer, and the second one is at the Fraunhofer Institute. And then there's a large effort in Japan and also in New South Wales. So in this slide, I'm going to just talk about the human studies. And it's an important lesson. Optobionics was a company in the US which has now failed because it didn't meet its FDA requirements. And what they did was they put solar cells, the Chow brothers were the stars, they put solar cells into the eye to stimulate the retina. And basically, as we know, the conversion is very low, and you're in various different light levels, and this was an underpowered device, so it never helped the patients, even though patients were implanted with these. I'll talk about our effort. Intelligent Medical Implants is a Swiss company, and Retinal Implants is the German company. And they're having difficulty because they don't have a long-term solution. Their devices will not last more than a few weeks or a month because of the packaging and the electronics. And so, and this surgery also this device is much more difficult to implant. So this is the device that the Argus One is a Second Sight Medical Products device with 16 electrodes that we have worked on and developed. And it's got a tiny camera that sits in the glasses, and it captures images. And this camera is about that size. These cameras have become very small. And then there's a visual processing unit, which you don't see, the size of a BlackBerry. And then this information is power and data are inductively coupled into the implant with a cable that goes in and stimulates the remaining neurons. Now, we have done extensive amounts of studying showing that when the photoreceptors are damaged, that the remaining neurons are intact. This was the first question. Well, if the photoreceptors are gone, then there won't be any other neurons. And this shows the transmission through the optic nerve. Now, you must be wondering, I was talking about the eye, how come the electronics are back here? And that is because we modified an existing cochlear implant. This was before our engineering research center, and it was difficult to do, and even before Wentai Lu's chip. And so what we had were electronics that worked for many, many decades, and what we did was change them and, in fact, took them to stimulate the neurons in the eye. This is what it looks like. This is a one-inch case, so it's about the size of the eyeball. Clearly, we can't put it in and around the eye, so that's why there's this cable that ultimately had to go into the eye. So, and this is how you strain, and this is another problem with the eye that you don't experience with the cochlea. It moves, so we have to put it around the eye and suture at different places to strain release it, so it doesn't end up pulling on the electrode in the eye. But you can see how we were able to put this in. And the features of this implant is that it works in the absence of photoreceptors, which is what the disease is. The chip electronics do not touch the retina, which is the heat issue. The electronics are back here. The only thing that's put in is the electrode array. There's software control, so the implant can be customized by the patient. So each patient requires slightly different parameterization and fitting. For example, subject 1 or subject 2, if you've been blind for 50 years versus 30 years, you may require different parameters on electrode 1, 2, 3. And then when you set each electrode, when you turn them all on at once, you have to do some more software parameterization. So this is what cochlear implant patients also undergo. So each person has their own software code because the level of damage in their eye or their ear is different. So you can't expect to have the same software helping everyone. It's the same general parameters, but there's some fine-tuning to it. It's wireless from the camera to the implant, so there's no wire going across the skin. Yes, from the electronic implant into the eye, it's hardwired, but at least there's nothing going across the skin, which is the big deal because that's how you can get these devices infected. And there's real-time visual processing from the camera, which we talked about. So, I mean, a lot of people try to put all the as I mentioned, people try to do it. We're doing it inductively from the camera. Folks have tried to do it with photodiodes, solar cells, but there's just not enough power. Even if you use intensifiers outside, you end up having to use 5, 6 suns type intensifiers. So that's why we're doing it inductively from the camera. So that once the camera captures it, then the information is, and the power is, and data is converted to our RF pulse. So we took maybe 5, 6 years of data, and with to the FDA, they approved this device, which is the Argus One, which is the 16-channel based on the cochlear implant. Believe it or not, you just can't take a device from the cochlear and expect it to be put in the retina without doing a lot of work to show to the FDA that it is a reliable device. We had the Institutional Review Board approval. Of course, if you do patient testing, you have to do it in accord with the Declaration of Helsinki. And the inclusion criteria was the patients had to have no or bare light perception. What do we mean by bare? A photographic flash. Nothing beyond that. I mean, and maybe they could tell that once in a while, not reliably. They had to have this condition, retinitis pigmentosa, which resulted in complete blindness. Obviously, no other optic nerve damage available for testing. Psychophysical testing and psychological profiling is important. I'll just take a second. If you've been blind for 3 to 5 decades, if you think this is the last chance or this is the last straw and this doesn't work for you or you're so desperate, these end up really affecting both the results and how you react to this device. So a fair amount of psychological profiling has to go into this, and the 6 patients have been implanted, and I'll share the results here. This is the first surgery of its kind in the world of February 2002. You can see here I am taking the device, putting it through the eye wall. All this hardware is normal to eye surgery, so don't think that that's part of this procedure. I'm sorry for those who can't watch eye surgery. Please close your eyes. But here's the device, and you can see where it's in the eye. But these electrodes are 500 microns, but they look gigantic inside the eye. A lot of regulatory people around me making sure that I'm following each step in the operating room. But we attach this device to the back of the eye, you'll see, through a very interesting way. It's a little tiny tack. And at this point, people are cringing, but in the back of the eye, there are no pain fibers. The outside of the eye, incredibly painful. You know, inside of the eye, no pain fibers. We're able to attach this device and leave it. And we tried for 3-4 years when I was at Hopkins, we tried all sorts of bioadhesive glues and et cetera, and it just doesn't work for this caliber device. Down the road, when we make the device a lot lighter, we can put different things. Now, in the audience, people may be somewhat smirking at the tack, but I'll tell you how important the tack and the close approximation of the electrode is in just a second. Here's the device. The beauty of having these devices, unlike cochlear implants of cardiac pacemakers, is when you come into the clinic, I can put a drop in and your pupil dilates, the front of your eye, and we can look right in and see exactly what this device looks like. No MRI, no CAT scan, no any of these things. And we can tell exactly where this is, and these are the electrodes in the back of the eye. Now this shows an OCT, optical coherence image, which is a 3D, and it tells us how close this electrode is. It's a light-based testing device, so of course where the electrodes are, it doesn't, the metal electrodes, it doesn't tell you the tissue underneath it. But this has been an incredibly important tool that's just come into ophthalmology. And why? Because we found that as the electrode, the height of the electrode, even as it starts to get into 100 microns or 200 microns, you see what it starts to do to the threshold required current for the subject to see. Now, a human hair is 200 microns. Can I surgically in the operating room put a device less than a human hair away from the retina? The answer is no. I can't see it visually. How in the world are we going to deal with this problem? And we were seeing it that if it was 250, these thresholds literally quadruple. So how do we address this? So we went back to engineering principles and we found something very interesting, which is the impedance. If you look at, this is at 1 kilohertz, and we do it across the band frequency, but you can see as the electrode distance increases, the impedance drops. So now, if I want it just to be 50 microns away or less than 100, I'm looking for impedances in electrodes 15 or higher. So I put the device in, have the guys in the operating room hook up temporarily and give me a readout on the impedances. It literally takes 10 seconds or 15 seconds, and they'll say, oh, your impedances are 5, push a little harder. A little is interesting. But this, you know, when you get this sorts of impedances, you're in good shape. And just to show you that this impedances actually do end up mapping to thresholds. So now we've solved a difficult surgical problem by using engineering here. And if you do get these devices in place, this is one of our subjects I'll be showing later. But over 6 months or so, you can see that this is the amount of current that is required is very low. This dashed line is very important. If we get anywhere near this, this is where you create electrolysis. So you basically come back 6 months later and there will be no metal electrode left. You've done a very good chemistry experiment. So this is sort of the window, the safety window, and by putting these electrodes close to the retina using impedances, we're able to have these devices last a long time. We're able to record from the visual, so we just don't rely on the subject saying I see something or I don't see something. We do psychophysical testing, which is I'll talk a little bit more about, but we also record, we can also record from the visual cortex. So we can put a little scalp electrode, just like the EKG electrode, we could just put them EEG electrode, and we can record here a response from the visual cortex. This is about, so February was this implant, so this is about 5 months later. You can see a very nice response, and this is the control, which doesn't show the response. So this was important. We wanted to find out whether electrodes that were next to each other really mapped that way. So this is the ideal map. If we took M1 and M3, these are the electrodes, and if we turned them on, you know, this is the subject's response, and you first look at this and you go, wow, that doesn't really look like this. This is not good. But the important thing is that the way we did this test, and you can see the M3 maps to the left of M1, L3 to the left of, so it preserves this sort of orientation. This would be terrible if the M3 was over here, etc. And the way this test was done is that the subject was asked to mark where they saw the spot and then come back to the center. And in fact, we did this test on ourselves. If you're in a completely blind room and you're back to the center, and every time somebody shows you a light where you go, you end up having something that looks like this. So this is very difficult to do in a completely blind room. And we found that in fact the spatial locations are very reliable. Here's one of our subjects who then can start to locate squares of this size in front of her. So this is the beginning of the training. Now, there's an important thing. Once we turn this device on, it just doesn't all of a sudden people are seeing and walking with it. There's a period of training and learning. And so this is how we begin, by showing these squares. And you can see that these are two subjects. The square can be in any 4 quadrants, so it has 25% if you're completely guessing. If you look at the trials, these subjects do far greater than just by chance alone. It does take them about 10 seconds. Now, why is it taking them 10 seconds, which you and I takes less than 1 second, is because their field of view is this big. Remember, we've only given them 16 electrodes, and they have about 16 degrees of field of view. So they're looking through a little hole, and they have to scan around. So there is a period where they... So now moving visual stimuli.
Left. Good. Ready, steady, go.
The computer is behind her,
Go.
and you can see the electrodes.
Down. That's good. Ready, steady, go. Right. That's good. Ready, steady, go. Right. That's good. Right.
So this was incredibly difficult in terms of the software we were talking about, because now it's not a static image, but you're moving, so you have to get the timings of the retinal neurons correct. But you can see that we can actually put the laptop behind her. We know exactly which electrodes are being stimulated, and so we can do a very good test. In any event, obviously the interesting thing is you could take the input from the camera or a computer. In fact, the first time I did this, it was anecdotal. I had the camera in my hand, and I was pointing at myself, and the subject was looking straight, and he was looking at where I was pointing at the camera, and it kind of becomes sort of bizarre and weird because it's not where they're seeing, it's where the camera is. Then you have to get used to not swinging the camera around because that's what they're seeing. But when they have it in their glasses, obviously they have full control over it. And with Armin Tanguay, we're working on a very intriguing project. We're putting the camera into the eye. So it'll be coupled with the eye movement, and we have some very good video for the first time of pictures from inside a camera in the eye looking outside. Of course, all preclinical is what I'm talking about. But again, the bar can move in 4 directions, and our subjects do much better than just chance. And here, this subject's been blind for 50 years. And here, this is not a demonstration of reading per se, but we're trying to see whether by moving their head back and forth, they can piece a complex type of geometry together. And again, this is just the little transducer, so it comes on and off. You know, you charge your camera and your batteries overnight or every other day, and they're able to tell. And this is amazing because this subject's been blind for 50 years, and we didn't think we would get this far. But it speaks to how much the brain is dependent on vision. In fact, if you look at the cortex, the processing part of your brain, a lot of it's dedicated to vision. So it's hungry, wants to reinstitute and use that part again. We wanted to see whether, if he could sit at a table after being blind for 50 years, could he really tell where the plate or cup, you know, how useful could this be? So, you know, could be a cup, plate, or a knife in front of him, and he was able to tell. Now, what was he seeing, people say? Was he really seeing a cup or plate? Well, what he sees is a saucer shape. When he sees a saucer shape of lights, that's a plate. If he sees a runway, that's a knife. So it's not like you and I see it, obviously, but it's enough. And this is, a lot of this was published, but you can see here's the object recognition: plate, knife, or cup. 3/4 choice test. If you're purely guessing, 1/3 of chance of getting right. These are the trials, and you can see that our subjects do far better than chance, and this was the finding the objects, etc. It becomes more interesting, just like the cochlear implant story. You know, will this help people who are blind from birth? And the answer is, it'll work. If it's like the cochlear implant, it will work beautifully if we put the implants in before age 10. In fact, cochlear implants work very well in kids if you get them in early. They work better than in adults. But if you wait till somebody who's been 30 or 40, then the brain, etc., is less accepting, and it could work, but it probably is not going to work as well as if you had sight before you got it into younger patients. So this is this is interesting. So we've always wanted to know whether more pixels made a difference, and I'll be quickly walk through this. But the multiple pixels, 14 versus single, and you can see that although there wasn't a great improvement in accuracy, because you're not making a big difference between one or multiple, the response time got a lot faster. So this was some early testing, but recently we've done something even more intriguing, and this is the data we submitted to the FDA, which is they said, well, what test are you going to, visual acuity is so important. These devices, no third-party pair is going to ever pay anything unless you show some visual acuity, even though we're showing all the videos I've shown. So we came up with this graded, which is very accepted, which is this graded square wave testing. And you can see here, this is with all 16 electrodes. You can see how there's 2 cycles, and when we do the testing, in fact, after 2 cycles, this is the subject's responses, that the responses fall into chance. Remember, the grading square can be vertical, horizontal, or oblique. So there are four ways, and it starts to fall into chance. Now what we did, so what vision is this? People always ask, what level of vision is this with the 16 electrode? In fact, it's 23 thousandths. Okay, I know, you guys, it's not 20/20 with 16 degrees field of view. Now, we know that patients can have unaided mobility at 21,020 degrees. So we're close, but we're not quite there yet with this 16 electrode device, and that's why it's not the clinical device. It's not the one that's going to be marketed or sold as the device. But what I wanted to really point out is that if we degraded it to a 2x2 array, group the electrodes, well, what happened? And that's an interesting thing. And now you can see after 1 cycle, the subject. So now we have a test. Now the vision is 28,000. Now we have a test that we can actually test these devices, which is important. Now, what if we scrambled the electrodes? So, and there they are, all in chance. So drop way down to just chance alone. So this is a great test we were able to get, and now we're going to be using this in our trials going forward. Now, So the Argus One, the 16-channel device, has good spatial, reliable spatial distribution. It's got better performance if you move the camera or your head. The impedances and thresholds are largely stable, surgically tolerated, and it speaks again to the incredible ability of the human brain to be able to make use of low-resolution images. And so we're moving in our ERC to making smaller devices that are completely implanted in and around the eye that are higher resolution. For example, here, this information, one day we envision, and we're working very hard on putting the entire device into the eye, so there are no cables going across the eye wall. And the challenges, of course, are both with the electronics and how you interface with the neurons, with the packaging, the electrode design, the circuitry, and also about the camera, as we discussed. And just to show you, here's where we really hit a chiasm. On the last 5 or 6 slides, I'll just show you that there was a big divide. This electrode was handmade, the one I showed you that was implanted in the eye. There are 2 people in the world that hand make them, and they're heavily guarded. If you want to go to a 60 electrode or higher electrode device, we had to microfabricate them. And this is work with YC Tai at Caltech, where we're using Parylene. You can say that we went from this handmade electrode to higher resolution devices, which are same size, but now are able to provide many more electrodes. In fact, these electronics and electrodes are so flexible, they're wrapped here around an edge, because remember, the eye is curved in the back, and so we need these electrodes to be curved. This is critical if FDA wants us to have these devices last 10, 20, 40 years. Well, I don't have 10, 20, 40 years to test them, and so through the Arrhenius process, we can elevate the temperatures high and result in a 4 or 5x acceleration on the failure mode. And here's a contraption we call the elephant eyeball, where we actually put the electronics in and are able to accelerate the failure modes. Here is a very great picture from our Engineering Research Center, which shows 1,000 electrodes. So this will allow about 20/80 vision, face recognition, and so this is where we're headed. And you can see the electrodes. This is microfabricated, and more importantly, these electrodes, now we can pattern them so they're exactly, or they correspond better to the underlying neuronal architecture. And you can see they're very closely, this OCT shows they're very close to the retinal tissue. This is the chip that Wentai Liu has helped develop for us, which drives these microelectronics, and in fact is at the heart of the 60-channel device, which I'll talk a little bit about. Temperature, big constraints. You cannot put a device in the body that has greater than 2 degrees Celsius rise. And so you can see here, working with Gianluca Lazzi at North Carolina State and others, that the temperature, in fact, is kept below the FDA requirements. So here's the take-home. Here's the Argus One with the 16 electrode, which I've shown. It took 15 years before the ERC. And here is Argus 2 with the 60 electrodes. It took us 5 years. So it has got 60 electrodes. It's 5 millimeters, roughly a quarter the size, 4x electrodes, 1/3 development time. You can see the electronics are placed around the eye. This one, the A60, which is now entering clinical trials, multi-center clinical trials in the United States and internationally, and we're training surgeons to do these implants. The electronic device and the electrodes are in. They're not, everything's not in the eye where I'd like it to be. There's still a little cable, but at least everything is around the eye. This surgery takes 2 hours. This surgery takes 7 hours. So we've made a significant jump here. And in order to get it into the eye, we're going to need to work with some packaging of these electronics so we can get it into the eye better. And this is some nanocrystalline diamond work that we're doing with argon, but we're also working with G-Tech and some other folks. Packaging is going to be the big next constraint for us. So in terms of timeline, the 16 pixel, we talked a lot about the results. This was a prototype, never meant to be out there because of the low resolution. We're thrilled with what we were able to get out of it, and our subjects are making good use out of it. But the Argus 2, which is the 60 pixel, which I just showed, is going to be the commercial device for mobility. And then the Model 3, the 1,000 pixels, I showed you just the electrode array. We have components, but we have to put it together to be able to do this. And if we're good, and we just like we did the 16.5, can we take the next step in 5 years as well is going to be the real challenge. And that's about when the ERC ends, 2013. So let's hope so. So anyway, just a couple other things. Obviously, this sort of project draws all sorts of attention. Being in California, especially, people say, well, hasn't this already been done? And why? And the other thing is, why do I have to wear these glasses to see? I'm like, listen, you know, everything is throw away the glasses. And so we've had lots of interest from museums, patient advocate groups. We have more than 150 each year news or media releases and interest. Of course, working with the FDA to help define a regulatory path. We have a planning symposium with them in 2008. And ethics of the body part, we had a great symposium in 2006 on this, because people always think you're controlling their brain and Big Brother's watching, et cetera, et cetera, et cetera. We're not doing any of that, but we still had a very interesting ethics of body replacement with this. And this is some educational initiatives, the last couple slides, where we had an international conference. This is the other Biomimetic Electronic Systems. Our ERC had at the Biomedical Engineering Society in 2007. And we had a full day. Actually, we took most of the people who attended on a bus, took them to USC, and showed them patients with implants. So there were tons of students. It was oversubscribed to come and see this. At the undergraduate and graduate level, we've developed tracks in neural engineering to help address this new area in medical devices. We've had thematic issues in leading magazines, as you can see here. And this is one of my favorite, is the K through 12. Here's our subject with one of these implants surrounded by the Murchison Elementary School students who are fascinated by even just Braille or what she does. I mean, they've never experienced or understood much of this. So with that, clearly the retinal prosthesis is a long-term, high-risk, high-payoff project. There's a lot of international interest with a fair amount of dollar investments from Germany, Japan, etc. And I like this because people often have called this project a moonshot to me. So, you know, I think in addition to the fact that I'm a big fan of the Apollo missions, it's also been called the moonshot. So I use that. And lastly, I would like to I would like to start off by acknowledging my family as a motivator. What I didn't tell you is that my grandmother went blind from diabetes, and I was going to be a neurosurgeon. The eye wasn't big enough, and I realized from her blindness how important it is to work in this area. Of course, working the various educations that I've gotten, excellent education from my mentors, my colleagues and students now. The layman, as I mentioned, is a continuous cheerleader. Just right when you want to quit the project, there's always somebody asking you and saying how fascinating this is. And of course, the funding agencies, NSF was there, got us started with Gil and the support he gave us for the chip development, and then the importance of the ERC program for my personal development and to take it further. Thank you for your attention.
Think forward. Think Research Channel.